Hi class, we are starting chapter 2. Chapter 2 is all about functions. We're going to look at the graphs of functions, all kinds of things that you can think of about functions. Functions are very important. It's probably the easiest, most effective way for us to think about these equations that we've been doing. So far we've been thinking of everything in terms of equations. I've thrown out the term function here and there, but we've still been kind of thinking of things as equations, right? Equations and functions are pretty much interchangeable, although functions have a little bit more, I guess you could say there's a few more restrictions on them, and there's a few more benefits to using a function versus an equation. Today we're really just going to go over the basics of functions, but as we move through chapter 2, we're really going to be analyzing functions and their graphs to a deeper extent, more so than you have in an algebra course. It's very, very important to understand functions because when we talk about things in calculus, we're always going to be talking about functions, okay? So, a function is really just a rule, okay? It's just like an equation, it's a rule. But here we're using an input and an output rather than thinking of it as an independent variable and a dependent variable, okay? So instead of talking about independence and dependence, we're really talking about what we're plugging in and what we are getting out, okay? I plug something into my function and the specific thing that I plug in gives me a specific thing out, right? So let's think about this in terms of some real world applications, things we come across all the time. So think of a soda dispensing machine, okay? Whether it's the old school ones where you put in $1, press a button and get a soda out, or the new ones where you put your soda, you have a variety of options, and you pick the type of drink that you want, right? So let's say we want to choose a particular flavor. That can be a soda, an iced tea, lemonade, water, whatever is available in this soda machine that we have, right? This is the input, okay? This is what we're telling the machine we want. We want this iced tea. We want this water. We want this lemonade. Okay, we're giving it some information in, okay? What comes out is our nice, cold, refreshing drink that we wanted, okay? Another example is your cell phone, okay? Your cell phone is a function. If you select a certain app, you press your Facebook app, you press your Flappy Birds, you press your whatever other app you have, your calculator function, right? That's the input. You're telling your phone what it is you want to access, right? The output is the app that you chose will open, and you can now use that app, right? And as you're using that app, you're going to give it more inputs. Hey, Google, search for this. That's an input, right? Google will now tell you what you want to look for, right? It'll give you your results back. If you're opening Facebook, right, you tell your phone, boom, I'm going to press Facebook. That's the input. What happens? Facebook opens. What's the next thing? I'm going to look at my feed. I'm going to swipe my finger up. That's an input. I'm telling my phone what to do. The result of that is that your feed scrolls down, right? Or unless you have your swipe the opposite direction. So that's an example of inputs and outputs, right? There's functions that dictate those apps and tells you, hey, if this is the input that's happening in this particular spot or what have you, then this is what I need my app to do, okay? A remote control for your TV or video game console is another example of a function, okay? Depending on what button you press is your input, that's going to control what happens out, right? If I press the volume button, the volume changes. The channel may change, a button menu might pop up, a character jumps, or whatever it is that I'm looking at, I'm giving it some input and some output is happening, okay? So, we generally refer to the input as the variable x, what we were calling the independent variable before, we're now referring to as input, okay? And the output, which we were calling y, we are now giving a bigger name, which is f of x, okay? So if we want to relate this f of x and this x to what we were doing all in chapter 1, which is x's and y's, we say that y is equal to f of x, okay? An equal way of talking about f of x is to think about it as the value of my function at the value of x. Okay? So again, our equations are basically changing name from y to f of x. That's really all that's happening here. Again, the f of x gives us a little bit more flexibility and a little bit more intuition into what's happening with y. Okay, so for example, in chapter 1, I would write y equals 2x minus 5. From here on out, we will be referring to it as f of x equals 2x minus 5. That's really the only difference, right? Y is equal to this thing. Now f of x is equal to this thing. Okay, so again, as I was saying, this notation has some benefits. Okay, one of those benefits is that it's very clear to understand what the input and output values are using this notation. Right, so let f of x be our previous example, 2x minus 5. If x equals 1, everywhere I see x here, I can replace it with the value of 1. So that means that inside of my function, I have f of 1. It's telling me that my input to my function is 1. I'm looking at the x value of 1 when I see f of 1. But what does f of 1 mean? Well, in my case, it means that everywhere I see x on the right side of my equation, the rule that I'm following, dictated by my function, which is 2x minus 5, everywhere I see x, I replace it with the input value of 1. Okay, so 2 times 1 minus 5 is 2 minus 5. That gives me a value out of negative 3. When I plug in 1, I get out negative 3. When I plug in 1 to my function, I get out negative 3. Okay, that's the benefit of this notation. So even if I have no idea what my rule is, I know that plugging in 1 gives me out negative 3. If we were to relate this to an ordered pair, this would give me the ordered pair of 1 comma negative 3. Okay, that would be the ordered pair to go with this. So that's the benefit of this rule, is that I can now easily see what my inputs are and what my outputs are, okay, without having to see what the rule is for the function. If I plug in x equals 3, okay, so 3 goes on the inside. Everywhere I see x in my rule, right, dictated by my function, I replace it with 3. I get 2 times 3 minus 5, or 6 minus 5, which is 1. So when I plug 3 into this function, I get out 1. Okay. If I plug in a value of lambda, right, a value of lambda looks like f of lambda, right? What that means is everywhere I see x, I plug in lambda. So my output is 2 lambda minus 5. Now you might be saying, Professor Williams, what the hell is lambda? It doesn't matter. It really doesn't. That's what's going into my function. And this is what I get out when I plug it into my function. Okay? Again, that's the benefit of having this function notation. I can plug in weird stuff, and what I get out is even other weird stuff, but that's fine because the function notation tells me what's coming in and what's going out, right? If I plug in something a little bit more understandable, a, for example, okay, it's just like lambda, it's just some constant, some value, right? If I plug in a, I'm going to get out 2 times a minus 5, or 2a minus 5. Let's say now that I plug in a minus 3 instead of a, right? So whatever this value is, let me subtract 3 from it. Well, what am I plugging in? I'm plugging in a minus 3. So what comes out then is 2 times not a, right? So everywhere I see x, I replace it with a minus 3. And if you notice, every time I plug something in, I'm plugging it in with the parentheses. Because a minus 3 is the quantity that I'm plugging in. Okay, if I don't use the parentheses, I would get 2a minus 3 minus 5. Here, since it's in parentheses, it's very clear that everything inside is multiplied times 2. So this turns into 2a minus 6 minus 5, or 2a minus 11. Okay, if I did not put the parentheses here to specify this quantity, I would end up with 2a minus 8 instead, which is not the same thing, obviously. Okay, so again, the values I'm plugging in, I'm specifying that with parentheses because that's the quantity that is being plugged in to my function. Okay, so f of a minus 3 is 2a minus 11. Okay. So if you haven't noticed, the input is on the inside of the function notation, and my output is outside of the notation, right? So if my notation is this, for instance, a minus 3 was inside of the function, 2a minus 11, the output, it's outside of the notation, okay? Input is somewhere inside of something, output is outside of something. So you can also think about it like this. My function eats a minus 3, so a minus 3 is inside of f's belly, okay? Then after you eat, stuff comes out. What's going to come out? 2a minus 11. That's the easiest way to remember, okay? 2a minus 11 is what comes out when you eat a minus 3, okay? So f of your input again is inside some notation, and your output is completely outside of everything else, right? It's on the right hand side, it's completely out. It's an output, right? This goes in, this comes out. For a relation to be a function, each input must go to only one output. Okay. So again, think of our remote control example. If I press the volume up, I expect the volume to go up. If I press the volume up a second time, it should go up. But what if I press it up a second time, but instead the channel changes? Well, that's two different outputs for the same input. I told the TV to turn the volume up twice. One time it worked, and one time it did something completely different. I would say, dang, my remote's messed up or my TV's messed up, right? A function should always work, okay? It should always work. It has to be reliable. If I plug in 1 to my function, okay, in this case, I only get one value out. I only get out negative 3. If I plug in 1 again to this function, I'm going to get negative 3 out again. If I plug in 1 again, I'm going to get out negative 3 again. Every time I plug in 1 here, I will get out negative 3. My function is reliable. It always works. It always gives me the same thing out. I will never plug in 1 to this and get something else out. Okay, so no matter what happens, whenever I plug in 1, it always comes out to negative 3. Okay. Now, just like when we're talking about equations, all of the possible inputs to my function is called its domain. And all of its possible outputs is going to be called the range. Right? So let's talk about a new type of function. Okay. So generally, most pre-calculus students have never seen what is called a piecewise function. Okay. A piecewise function is just that. It's a function that is defined in pieces. Okay. Basically, I say from this value of x to this value of x, my function looks like this. And then from this value of x to this value of x, my function looks like this. And I can do that for as many pieces as I need to represent whatever's going on. Okay. So again, our function is basically defined in pieces over different intervals. Okay. So here's an example. If I'm going from negative infinity to negative 4, including negative 4, this is the value of my function. After negative 4, but not including at that point, I have a value of 4 all the way until I get to 2, right? But not including 2. And then once I'm at the value of 2, I have the value of 1/2 x squared. And then from there all the way to infinity, this is the values that my inputs put out. Okay? That's a piecewise function. It is a linear function, it's a constant function, and in this case, a squared function over its entire domain. Okay, and depending on what value I'm plugging in will tell me what value I need to look at for the output. Okay, so again, notice that the input values, they never share the same input value. Okay, if I plug in negative 4, right, the endpoint here, the endpoint of, so negative 4 is an endpoint here and an endpoint here. But negative 4 doesn't work for this one. Okay, when I plug in negative 4, I'm looking at this equation. Okay, even though there are two separate places, 4 is included here, 4 is not included here, right? Because of the open bracket. When I'm looking at 2, I'm looking at 2 for this case, right? This is the one that I would go to because of the closed bracket. I would not go here because 2 is almost included here. All the values leading up to 2, but not 2 itself, right? So make sure you're looking at the right function for whatever input you're looking at. Okay, so again, notice that the input values that share 2 different functions never exist for both functions at the same time, right? They only exist for one. I can't have a closed bracket here and a closed bracket here, because then I might have 2 separate outputs for the same input, and that would not be okay, right? So in one function, it will be included in the interval, and in the other, it won't, right? So in one interval, it has an open bracket, in the other, it has a closed bracket, okay? So that way, my intervals don't overlap, okay? The intervals and the functions above them don't overlap. So there's no overlapping parts, but there can be gaps between the outputs. Right. So we'll see an example of a piecewise function, the graph of a piecewise function in, I believe, the next video. Right. So there's 4 ways to represent a function. We can do it verbally with words. We can do it algebraically with our function notation that we're just talking about. We can do it visually with the graph, which is, I'm sure, what you would like to have seen for the last example for the piecewise function, okay? And numerically with a table of values. So all of these we've gone over at some point, okay? Numerically with the table of values is how we generally talk about equations, which now we're calling them functions, when we first learn how to graph, right? So in this textbook, in this class, we will go over all 4 of these, right? I might give you a function as a table of values and ask you to analyze these table of values. I might give you a graph and we analyze the graph. May give you the equation, which is going to be probably the most often. Verbally, with words, would be pretty much the same as a word problem, right? So again, we're going to utilize mostly these last 3 cases. And I could give you all of them, or I can give you 1 or 2 or, you know, however many I feel is necessary, but you should be familiar with looking at all the forms of a graph. Okay, so let's look at an example. So let's consider the function f of x equals 1 over x. If we talk about all the things we've done so far, the domain of f of x is basically anything that does not make the denominator 0. Okay, so any real number such that the denominator is not 0. So any real number that's not 0. The range, this can be any positive and it can be any negative, but it cannot be 0, okay? So the output set is all real numbers except for 0. There's no way to make this 0, but I can make it any number as close to 0 as I want, right? Here we have a weird function thing. This is actually called the difference quotient. This is extremely, 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 extremely important in calculus, okay? But for right now, I'm just going to ask you to simplify this, right? So if this is my function and I'm asking you to evaluate f of x plus h minus f of x over h, now we're doing some stuff to the input and the output of my function. So it would look something like this. Everywhere I see x, I replace it with x plus h. So that's 1 over x plus h. I'm going to subtract to that f of x. So f of x is 1 over x. And to all of that, I'm going to divide it by whatever this value of h is, right? So this was called the difference quotient, will look like this. I'm not done, however, because this is the same thing as a complex fraction. So I want to simplify this complex fraction. Again, I can do that by adding this together into a single expression, right? A single rational expression, and then multiply it by the reciprocal of h. Or I can clear out the denominators. So if I'm clearing the denominators, I'm looking for the LCM of the innermost fractions, which is x times x plus h. So I multiply both of those times x plus h. So h times x plus h looks like this on the bottom. Okay. For the numerator, the only thing that was missing was x. X plus h was already there, so that cancels. So this turns into an x. Here x is already present. The only thing missing is x plus h. So when I multiply it by the LCM, the x cancels and the x plus h stays. Okay, then when I simplify from here, I will get x minus x, so that'll cancel. but I'll also have a negative h here. Okay, so I'll have a single value of negative h on top and h on the bottom. Those two h's will cancel, but it'll still be negative, so I got a negative 1 over x times x plus h. Okay, so verbally we can say the output is equal to the reciprocal of the input. Okay, 1 over x. The output is equal to the reciprocal of the input. Okay, so I'm plugging in x, but it's the reciprocal of x, right? The output is equal to the reciprocal of the input. That's me verbally describing this function with words. The graph of f of x looks like this, right? So we have the verbal representation, the graphical representation. We're given the algebraic function notation, right? The algebraic representation. The graph looks as such. Okay, so notice there is nothing at 0. Okay, my function never equals 0. Okay, and I cannot plug in 0, so there's no outputs along the line. Okay, as a table of values, I have my x and my f of x. I plug in a value. This is what I get out, right? Oops. Plug in a value. The reciprocal is what I get out. I plug in 2. The reciprocal is what I get out. I plug in 1. The reciprocal of negative 1 is negative 1. I can't plug in 0. Let's say I plug in something close to 0, like 1/2. I get out the reciprocal, negative 2, right? It's a reciprocal function. If I do try to plug in 0, it's undefined because I can't have 0 in the denominator. Right? Same thing if I plug in positive values that are very small, I get out very large values. Right? 1 is 1, 100 is a very small value. Okay, so again, very similar to those to what we were talking about in the last video, 1.12 for the modeling variations. Okay, if I plug in something large, I get out something small. If I plug in something small, I get out something large because of the nature of the function. Right? So that's it. I'll see you guys on the next video.